Welcome back to our third of four videos on IP addressing. In our first video, we took a look at basic binary numbering, how to convert between decimal and binary. In our last video, we took a look at basic subnetting, and basic subnetting addressed questions such as, if you want to subnet a classful network into a certain number of subnets, what subnet mask should you use? And how many hosts will each of those subnets accommodate? Those are the kinds of questions we answered last time. In this video, we're going to get into advanced subnetting, where we're going to ask the question, now that we've subnetted a classful network into all these subnets, and we said that by applying a 27-bit subnet mask, we're going to be able to create a certain number of subnets. Once we do that, what are those subnets? What are the address ranges? Because in our design, after we say that we're going to be able to create however many subnets, we need to know what IP addresses to assign to devices in those subnets. That's what we're going to do in this video, and then in our final video coming up next time, we'll take a look at IPv6, because our discussion thus far has primarily been IPv4. But let's get into advanced subnetting, and we'll start out with a fairly basic example. Here we have a Class B network. We know it's Class B because of that first octet, 172. That's in that range that we should memorize from the last video. It's in that range of 128 through 191. That tells us this is a Class B network. And a Class B network has a default. It has a classful subnet mask of 16 bits. However, let's say that we want to carve this up a little bit and we want to subnet this so we can have different address spaces connected to different router interfaces. And a common way that we might do this is to use a 24-bit subnet mask. If we use a 24-bit subnet mask, the default mask of a Class C network, what we're doing is, in that third octet, we're simply adding 1. We start out at 172.25.0.0/24, and then for the next subnet, we have a 1 in that third octet, then a 2 in the third octet, and on and on and on. And the last subnet that we create with the 24-bit subnet mask is a 255 in that third octet. This looks hopefully fairly intuitive, and you see what we did. We counted by 1 in the third octet. That might seem straightforward, but it seems to get a bit more confusing when we start having 27-bit subnet masks or 22-bit subnet masks, a subnet mask that doesn't end at an octet. But from this simple example, I want you to notice something. We were following a set of rules to create these subnets that we can follow to calculate more complex subnets. You see, what we did, we determined in which of those 4 octets are we going to be counting. We're going to be incrementing one of those octets, and we said it's the third octet. And what number did we count by? We counted by a 1. And I've got some terminology for you right now. The octet that we incremented, in this case was the third octet, that is called the interesting octet. And the size of that increment, the number that we counted by, that's called the block size. We're going to be able to determine the interesting octet and the block size for any of our subnets and do something very, very similar. And as I was deciding how to present advanced subnetting, there are so many ways to do it. There is a very rigorous mathematical approach to doing this calculation. There are several shortcuts out there, and you might already know a shortcut, and if you're good with that, you might want to stick with that. But here's what I thought. I don't want to give you too many shortcuts because I'm afraid that they'll kind of blur together, and I don't want to create confusion. You really don't need more than one shortcut. And I decided not to go the rigorous mathematical approach. For one reason, you don't have time for it on the exam in many cases. I don't want you to feel rushed. I want you to be able to calculate these networks very, very quickly. As I was thinking about this, I was reminded of when I was in college. I got a Bachelor's of Science degree in electrical engineering, and as I was going through those engineering classes, a significant percentage of the lecture time was my professors standing up at the board and going through these mathematical proofs of why a certain formula was correct. And maybe this is why I was an engineering major, not a math major. My perspective was this. My perspective was, I trust you. You don't have to prove it to me. Just give me the formula so I can do something useful with it. That's the approach that I decided to take here. I want to give you a super useful set of steps without getting into the elegant mathematical proofs behind it. And as a result, you can take this tool and be very efficient in any sort of real-world or exam design scenarios. Let's get into it. The first thing we need to do is to determine that interesting octet. Here's the definition. The interesting octet is the last octet to have a 1 in the subnet mask. In our example, we had a subnet mask of 24. That translates into 255.255.255.0. If we were to write that in binary, we would have 8 ones and a dot, 8 ones and a dot, 8 ones and a dot, and then 8 zeros. The last octet to contain a 1 is the third octet. Here's what that 24-bit subnet mask looks like in binary. The last octet to contain a 1 is the third octet, and we're going to call that the interesting octet. That's step 1. The second step, now that we know in which octet we're going to be counting, what is that increment size? What is the block size? The block size can be calculated with this formula. It's 256 minus the value in the subnet mask's interesting octet. Not the network address's interesting octet, but the subnet mask's interesting octet. And in this case, it's 255.255.255.0. What's the value in the third octet? 255. The block size is therefore 256 minus 255. That's going to give us a 1. That's going to give us a block size of a 1. We said we had 255 in the interesting octet in our subnet mask, 256 minus that 255, that gives us 1. That tells us we're going to count by 1 in the third octet. That's what we were doing. We were saying we're going to start out at 172.25.0.0/24, the very first subnet, by the way. That's when you set all of your borrowed bits to a 0 in the network address. So in this case, it's going to be 172.25.0.0/24. That's the first network. Then we're told that we're going to increment by 1 in the third octet. So then we have 172.25.1.0, 172.25.2.0, and on and on and on until we get through the last network of 172.25.255.0. Now we know what those address ranges are. We took a Class B network and we subnetted it. We carved it up into 256 subnets. And this goes back to the formula we learned in the previous video. The number of subnets we create is 2 raised to the power of s, where s is the number of borrowed bits. And in this case, we had a 24-bit subnet mask. A Class B network has 16 bits in its subnet mask by default. Therefore, the extra bits, the borrowed bits, the bits beyond 16, was 8. 2 raised to the 8th power, that gave us 256 subnets, and now we know what those subnets are. The final question we need to ask is, what is the range of usable addresses within each of those subnets? Do you remember when we were calculating the number of hosts per subnet last time? We were making the observation that the host bits could not all be set to zeros, because that's the address of the subnet. Similarly, the host bits cannot all be set to a 1, because that's the directed broadcast address for that subnet. So we want to ask, what is the usable range of addresses for each of these subnets? Let's see how we would do that calculation. The subnet is simply all the host bits set to 0. So 172.25.0.0/24, that's going to have a directed broadcast address where we simply set all the bits in that last octet to a 1, 255. If we exclude 172.25.0.0 and 172.25.0.255 from that first subnet, we're left with the usable range of addresses as you see on screen, 172.25.0.1 through 172.25.0.254. Similarly, 172.25.1.0, that's the network address. 172.25.1.255, that's the directed broadcast. Everything in between, that's the usable range of addresses. To sum up the steps we went through, this is the key point I want you to get from this video. Number 1, determine what is the interesting octet. That's the octet that contains the last 1 in the subnet mask. Step number 2, determine the block size. And the formula for that was 256 minus whatever the subnet value is for the interesting octet. Thirdly, determine the first subnet by setting all of the borrowed bits, all the bits beyond the natural mask in the network address. Set all those bits to 0, and then you just start counting. Start in that interesting octet and start incrementing by your block size. And once you have calculated all of your subnets, then you eliminate the first IP address in that subnet and the last IP address in that subnet, because the first one, that's the network address or the subnet address. The last one, that's the directed broadcast address. Everything in between, that is your usable range of IP addresses. Using these steps, let me challenge you with a scenario. Let's say that you wish to apply a 26-bit subnet mask to your Class C network, 192.168.0.0/24. You want to apply a 26-bit subnet mask to that network address space. My question to you is this: what are the subnets, and what are the usable address ranges in each subnet? You might want to pause the video here and go through those 5 steps. You might want to back the video up if you didn't write down those 5 steps. And after you finish your calculation, come back and join me and we'll go through the answer. All right, how did you do? Let's take a look at the answer. The first step is to determine the interesting octet. Well, we've got a 26-bit subnet mask, which looks like 255.255.255.192, and we learned how to do this in our first and second videos on IP addressing. And what's the last octet to contain a 1? It's the fourth octet. We have 11000000 as the binary bits in that last octet. That's step number 1. We've determined that the fourth octet is the interesting octet. Step number 2, what's the block size? Remember how we calculated the block size? It's 256 minus whatever the subnet value is in that interesting octet. In this case, it's 192. What is 256 minus 192? It's 64. We know that that's what we're going to be counting by. Let's see what the first subnet is. We're going to set all the borrowed bits to a 0. That's going to give us 192.168.0.0/26. Now we can start counting by the block size in the interesting octet, and that's going to give us, well, we know the first network, 192.168.0.0, but as we start counting by the block size, now we have 192.168.0.64. You see, we're counting by the block size in the interesting octet. So that fourth octet then becomes 128 and 192. And finally, we want to determine the usable range of addresses. The network addresses that we listed on screen, those are the subnets. We cannot use those. That's the address of the wire, it's called. And if we were to set the last 6 bits in these subnets to a 1, that would be the directed broadcast address for that subnet. You don't really have to do the binary math to figure that out, by the way. For example, take a look at the subnet 192.168.0.0. If I want to know what the directed broadcast is, I don't really have to do the math and see, well, what would 6 1s in binary be? Now, what I can do is just take 1 away from the value of the next subnet. You see the next subnet is 192.168.0.64. Just take 1 away from that. That gives me the directed broadcast address of the previous subnet. Anything in between the network address and the directed broadcast, that's your usable range of IP addresses, as you see laid out for you on screen. I've got one more exercise for you. In this exercise, we want to make sure that these 4 clients have appropriate IP addressing. In fact, we're told that one doesn't, so this is a troubleshooting exercise. I want you to determine which PC is assigned an incorrect IP address. It has an IP address that doesn't belong to the subnet of its VLAN. Notice the addressing on screen. We're taking a Class B network of 172.16.0.0/16, and we're subnetting it. We're using a /20 subnet mask. In other words, we've added 4 bits. We have 4 borrowed bits. 2 raised to the 4th power is 16. There are 16 potential subnets that we have carved out, and we're using 2 of those on screen. And what we need you to do is to determine which client does not live in the appropriate subnet. And the way you're going to do this, you're going to determine what are those subnets, and what is the subnet of each VLAN, and check to see if a client lives in the usable address space for a VLAN. And I want you to find the one that doesn't fit. One is inaccurate. Again, you might want to pause the video and come back and join me to check the answers. Let's check our answers for this exercise now. The first thing we do is to determine the interesting octet. The interesting octet is based on the subnet mask, which with a 20-bit subnet mask is 255.255.240.0. What's the last octet to contain a 1 in the subnet mask? It's the 3rd octet. That's our interesting octet. The next step, determine the block size. What are we going to be counting by in that 3rd octet? It's 255 minus the subnet value in that interesting octet, which you can see on screen is 240. What is 256 minus 240? That's going to be 16. If we set all of the borrowed bits to 0, we had 4 borrowed bits, setting all those to 0 gives us what the classful network looks like, 172.16.0.0, except this time we have a /20 subnet mask. Now we can start counting by 16 our block size to see what are all of those subnets. We're going to count by 16 starting at 0. So we'll say that we have networks of 172.16.0.0/20, and then as you see on screen 16, 32, 48, and on and on and on. Finally, we want to determine the range of usable addresses by excluding the subnet's address, the address of the wire, and the directed broadcast address. And we're only interested in 2 specific subnets here, one for VLAN A, one for VLAN B. Take a look at the router interfaces address. For VLAN A, we have 172.16.90.255. That looks like a directed broadcast address almost, doesn't it? Because it has a 255. But notice, it's not, because we're not using a 24-bit subnet mask. We're using a 20-bit subnet mask. Let's ask ourselves, in which of these networks do those router interfaces lie? The router interface for VLAN A is 172.16.90. Which one of those on screen does it lie in? Yeah, it's in that range of 80 through 95 in that third octet. So VLAN A is really using the network address space of 172.16.80.0/20. And 172.16.90.255 happens to lie in that address space. What about VLAN B? 172.16.208.255/20? That lives in the 172.16.208.0/20 subnet. We now know what the subnets are for VLAN A and for VLAN B. Let's see what the subnet each of the PCs belong to. Here on screen I've written out the range of usable addresses for VLANs A and B. Which one doesn't correspond to the client IP address? And as you can see on screen, client 3 over in VLAN B, it has an IP address of 172.16.206.5/20. That's not in the range of usable addresses for VLAN B. So that's the client that has an incorrect IP address. That's going to wrap it up for our advanced subnetting video. By the way, if you want some additional practice with this, there are a variety of subnet calculators you can download from the internet. One that I personally use, I don't have any affiliation with them, but just one that I like to use is from solarwinds.com. You can go into the downloads area at solarwinds.com, and they've got a really nice subnet calculator. It does everything that I need it to do. And there are others out there as well, but that's a starting point. You can go check out theirs if you like. That's going to wrap up our third video. We've got one more video in this IP addressing series, and it's on IP version 6. We'll see you back for that next time.